you.
Can you hear me?
Yeah, yes, I can hear you. Good morning.
Okay, my apologies. Yeah. Good morning. How are you doing?
Yeah, we are fine. Thank you. I think we are all set.
Great. Great.
We'll just wait for 2 minutes as Amit sir has to start the.
Not a problem. Not a problem at all.
I think we are getting echo. Amit sir?
Yes, sir. I have started with live. Sir is just joining with us.
Here we are getting the recording.
Shilar sir.
Yes, sir.
हा ऐकू येते ना?
हा येते ऐकू. Yes, I can hear you.
हा बरं. मी काय हे करायचं पहिलं स्टार्ट?
Yeah, you can welcome once we set up the system.
Okay, okay.
Yeah, we done with sir. We can start.
अमित सर ते युट्यूबचा इको इकडे पण येतोय. Amit sir, are you there?
Yes, sir.
Can we start?
Yes, sir. You can start, sir.
तो इकोचा प्रॉब्लेम गेला ना?
नाही तुम्ही दोन लॅपटॉप शेजारी.
YouTube one is also started.
Yeah, YouTube is also started. You can start now, sir.
सर ते परत थोड्या वेळाने आपल्याला रेकॉर्डिंग ऐकू येते. ब्रॉडकास्ट मुळे होते का?
एक मिनिट. तुम्ही स्टार्ट करा. माझा एक
Chris, are you set?
Yes. Yes.
So should we start?
If you are ready, I am.
Yes, we are all ready.
Right.
Our principal sir, Dr. Pradeep Mane sir, has also joined the meeting. Initially, I would request him to say few some words.
Sure.
Yeah. Hello.
Yes, hello.
Can you hear me?
I can hear you, yes.
Yeah. A very good evening, and maybe participants from all over the globe. whatever time over there may be, maybe morning or whatever. So first of all, I would like to welcome all the participants, and we are very much obliged to have a speaker like Chris today for this webinar on improving efficiency, power quality using software-defined electricity. Today, at least in India, this area is coming up very rapidly, and the industries are realizing the importance of doing all these things. Am I audible?
Yes, sir.
Yeah. So indeed, we are very happy to have Chris with us over here. I would also like to thank him on behalf of our management, our Honorable Secretary Sri Malojiraje Chhatrapati, and all our teachers. I would also like to take this opportunity to thank the coordinator of this event, Mr. Sachin Shelar, who is working in this area, and his work has been well appreciated by all the industries where he has worked. So with this, I like to once again thank all the participants for joining this webinar, and a warm welcome once again to Chris, to you. Thank you. Thank you very much.
Thank you, sir.
Thank you very much. I appreciate it.
Yeah, Chris, I will just take 2 minutes to show some slides, and then we'll start. So is it okay?
Of course. Yes, please. Thank you.
Yeah. So first of all, on behalf of AISSMS Institute of Information Technology, I welcome all the participants for this webinar. As you can see in the photograph, this is our campus at Pune, All India Sri Shivaji Memorial Society. It's a premier heritage group of institute, which was established in 1917. And there are many professional colleges as well as schools are being run by this society. We are guided by the His Highness Sri Shahu Chhatrapati Maharaj, who is our president of AISMS Society. Also, we are getting guided by the Vice President Sri Sambhaji Raje Chhatrapati, then Sri Malojiraji Chhatrapati, who is the Honorary Secretary of AISSM Society, and Sri Suresh Pratap Shinde, Honorary Joint Secretary AISMS Society. The vision of our institute is to uplift the common masses by rendering value-added education, and this webinar is one of such initiative for this. A quick introduction to our Department of Electrical Engineering. Our institute that AISSMS Society started in 1999. And in this department, we have started a cell, Power Quality and Energy Conservation Cell. The main objective of this cell is to give power quality training, not only to students, but also to industry. As power quality is a new subject, we need to give training to all the stakeholders. So our PQ cell is doing one part on that. Then we are also conducting power quality audit professionally for industries. In that, we are conducting harmonic audits, as everyone is aware, especially in India and in Maharashtra, the harmonic is being discussed a lot. Then reactive power audit, as KVH billing is coming, there are penalties for lag, lead. So that is also we are doing. Transient audit, likewise, we offer power quality consultancy to industry. We are also into energy and power quality monitoring system, because as everyone knows, if you can measure it, you can manage it. And lastly, you have to start with electricity bill. Power quality comes later on, but first you should understand electricity bill. So electricity bill analysis is also one of the part. We have reputed instruments, class A instruments in our lab. Those are well calibrated, and many of our members are well trained onto that. Then coming to our today's speaker, I'm very happy to introduce to you our today's speaker, Chris Doppler. He is co-founder of 3DFS and SAM Controller. I will just give 2 lines about 3DFS. It is headquartered in Pittsboro, North Carolina, USA. and a very unique engineering group, and they have invented a real-time parallel computing method, and they are using it to control. And that's why you must have seen the topic is a software-defined electricity. So it is a very interesting topic, and I'm sure that Chris will cover all the points in detail. The session will be in three parts. Initially, he will cover presentation. Then he will show actual demo of the software defined electricity. And lastly, we will have a question answer session. Before Chris starts, I would like to give some general instructions. All the participants, please mute your audio if you are not done. Also, stop video if it is on, so that bandwidth will get a good bandwidth. If anyone wants to ask question directly to the speaker, please click on the raise hand button. This kind of button might be there on your screen. We will unmute you during question and answer, and you can directly talk to Chris. Alternatively, you can also post your question in question answer section, and at the end I'll be reading those questions to Chris. We will try to cover maximum number of questions. Feedback link will be shared at the end of the question and answer section. This will help us to give you e-certificate, as well as presentation, if shared by the speaker, will be given to your register email ID. Please note that write your name and your organization association properly in the feedback form, so because that will be printed directly onto the e-certificate. Please do not post any message regarding feedback link. It will be given at the end of the question answer. Please concentrate on the webinar. And feedback link will be closed after 30 minutes. So I am sure all of you will go through this instruction, and we'll have a very good learning from Chris. So thank you all of you. Now Chris, floor is yours.
Thank you very much, Sachin. I appreciate it.
Amit sir, can you make Chris? Yeah, is your presenter, Chris.
Got it. Okay, and now does everyone see the presentation?
Yeah,
okay,
we can see.
Great. So to start out, thank you so much, Sachin. Thank you very much to the AISSMS. I certainly appreciate the opportunity to talk about this. What we have is a very unique technology, and it's a very exciting right in the power quality space. So there's likely to be a lot of interest and a lot of questions. I'll be happy to answer everything I can. If some of the questions get really technical, I can write them down and get back to you after I speak to an engineering group. But for the most part, I should be able to answer everything for you. So thank you. To start out, to give you a little bit about 3DFS, we are a research and engineering group. We are based, as Sachin said, out of North Carolina, and we have a history of groundbreaking patents. The original patent that we started in the United States was when 802.11 was declassified from the US military. It took watts of power to communicate. The phones were really big and had large batteries. What our engineering group did was develop spread spectrum communication and wireless power antenna management. It was 3 separate patents that exited to Texas Instruments, and it took that watts of power to communicate and dropped it down to milliwatts of power. When any cell phone on the planet is purchased, we get 7 cents because of that intellectual property. And that was the beginning of our organization. After that, we focused on sensing, pathogen detection. If you recall the anthrax attacks that occurred many years ago in the United States, at that time, they were not 100% sure that was anthrax. They assumed it was based on the response in the dogs and the people. But they actually had to send a sample off, which was replicated over 26 days before they could definitively identify it as anthrax. And what our engineering group did was took that challenge and invented what is called the single electron transistor. And it was able to detect the electrical signature of any protein or virus or microbe or bacteria in pretty close to real time. So the anthrax, it was the test for the anthrax revealed that it detected anthrax and 26 other analytes in less than 10 seconds. And then it exited to general dynamics and is used for pathogen detection on the front line. And after that venture, we started to focus more on electricity as used in the grid. And in looking at the losses that exist, we did a whole bunch of research into the measurement of electricity. And that is what got us started on this particular venture with the money and the ideas from the previous exits. We not only invent the IP, we also do all of the manufacturing and production here in North Carolina. We go from a research-friendly low prototype production line all the way to mass manufacturing. So we like to control all of our products from soup to nuts so that we know we're delivering exactly what we say we are. Our core innovation, there's lots of technical know-how and innovation within these products, but the core concept behind it all is a new method of computing. We call it task-oriented optimal computing. Traditional computing power is limited. If you buy a processor, regardless of the processor, it could be an FPGA, an ARM processor, it doesn't matter. You are limited to the amount of computing power you have based on the hardware and software in that processor. What we do is we purchase the hardware and then we remove the software and replace it with our own, which is much more efficient and effective at controlling the processor down to the amount of energy that it takes to open up and close the transistor gates. This allows us to extract much more computing power out of a processor, sometimes thousands of times more computing power. In addition, we can parallel multiple processors together, and we have no ceiling on the amount of computing power that we can apply to a situation. We have unlimited scalability at 98% efficient computing power. And this is our core innovation, this efficient, flexible, parallel computing method. What we have done is applied this computing method to the physics of sensing. There are enormous data handling and data processing challenges when it comes to the physics of sensing. We have solved those problems. The initial or the major problem is conversion from analog to digital without error. So what our computing method does is it addresses all of the data quality issues, so your ranging and sorting and jitter, upon acquisition and during conversion. It's all one act. In a single conversion, it's error-free. In addition, because we have this precise sensing with computing, we can synchronize the timing across any number of sensors. So in a system, the sensors can acquire the exact moment in time with 100% certainty, error-free data, providing a full 360 picture of a system. And this is what allows us to, it just provides us visibility that is not normally there with modern sensing. We take a specific focus on electricity sensing because electricity is not just power. It is information about all all of the power in addition to that power. So everything that consumes electricity does so with a very unique, specific pattern, more unique than a thumbprint. If you have 1,000 different televisions or 1,000 different motors or whatever, pick the electronic. If you zoom out and look at the electrical signature, it all looks the same because of the circuit boards or the windings or whatever is internal are the same. But when you have this electricity microscope that we have, you can zoom in to the electrical signature and you see that they are not the same. Each of the internal components for an electronic has a tiny variance or tolerance difference. The wire thickness is not the same and uniform throughout the entire wire. The solder placement is different every time a component gets soldered. And each of these contributes a delta, a difference to the electrical signature, if not even just a tiny bit. And what we have invented is a method with which to see all of that. And when you're able to dive in as much as we can with electricity, it opens up not just visibility, but the ability to interact with that. So one example I always give is in flipping a switch. If I need to flip a switch in the building next to us, the way it's done today is I have to send a signal to flip that switch. And when it switches, a signal needs to be sent back to me to let me know that the switch flipped. And what I challenge you to do is sort of change your perspective, because if everything has a unique electrical signature and the system knows that electrical signature, then now when that switch flips, the system knows in real time that that switch flips with no need for a second layer of communication to alert. And this is the fundamental concept of what we're doing. Most control systems focus on secondary parameters. They're used in, relays and switches and timers, but those aren't real. That's not primary parameters. And so now that we have this method of sensing, we're able to go into control systems and sense for primary parameters and use those for control. And this is our advantage in the control system world. Using electricity as feedback and communication upgrades the speed and accuracy of control systems to real time. And this is our control method that we have applied. What you see on the screen, what we do is very complex, but it really does boil down to a very simple equation. A plus B equals C, where as C is defined as the perfect machine performance. It doesn't matter the machine. All of them use physics and science. That's how they were able to be built and leverage what they do. A control system needs to interact and deliver that perfect machine performance. So if C is defined as perfect machine performance, A has to be defined as what is the measurement, what is the machine doing presently, right now, in this exact moment, without any error. What is it doing? And that part has been missing. We have invented that part. And now that we have invented that part, our control systems, now that we know what is going on in real time, we know exactly what should be going on. The delta is really just the control action. And this is the concept that we take to everything. Solve for B, and then scrutinize any data, any delta between what actually happened versus what should have happened. Right? And based on that, it can make an adjustment the next time that system comes up or the next time that event comes up. One enormous advantage to this method is that it's edge computing embedded into control systems. All of the science is embedded into the control system and operating in real time. There is zero need to connect to the internet. It's a complete edge control system, therefore it is fully cyber secure. Another advantage of this method is by embedding the computing into the control system so that all of the analytics are being used in real time for control. To get any data out is a simple serial port out. There's no ability to control the system from the outside, therefore making it even more secure, and also providing access to data and analytics of the system in real time. Now, what I stuck on the bottom right there, we have 3DFS, but we also have SAM controllers, because we take this application of real-time sensing and control and we apply it to any machine control system. Water pumps, like the purpose of a water pump is to pump water. But when you bury it 1,000 feet underground, if water's there, great, it's pumping. If water is not there, the pump burns out, because there's no real-time intelligence as to what is going on. And so we built a controller that provides that water pump the intelligence of whether water's there or not, or whether there's ground current or not, or whether there's sediment in the impeller, because all of these can be identified through the electrical signature. We've got compressor controllers, new ways to level water, sewage, irrigation. All machines are not designed presently to work in real time, and we're upgrading all machines too. And this is what the core mission of our company are. What I'm going to talk about today and give you a demonstration of is software-defined electricity. It is this same method of control, only applied to power electronics. What you see on the screen, the vector Q2, this is a 60 kilowatt, 240 volt, 208, 240 volt power controller. It uses 120 watts to correct 60 kilowatts, 98% efficient. It is installed in parallel. There are 3 flex coil transformers. This image is slightly out of date, my apologies. These are split core, but now we use flex coil. But there are 3 flex coil current transformers on the incoming phases. There is a voltage connection at the breaker on each phase, and then ground and neutral are wired. And that's the installation. It's fully in parallel. The device senses through the current transformers. It contains the power electronics within the vector. There is a source of inductance and a source of capacitance within the device. And that it injects the source of inductance, or it injects capacitance or inductance through the voltage connection. You see here on the bottom, in a very, again, I apologize for the simplicity of this. Obviously, there's way more involved, but the problem that has always existed, we know what perfect power should look like. That's mathematically defined. What we've never been able to see is what power actually looks like. And so this is always the same concept for power as it is for compressor, as it is for water pump. You need to know what it is today in real time, and then you can make the correction and control. There's a lot on this slide, so I'll just briefly speak about it. The reason why controlled power is so important. The losses that exist today, most of them do not need to be there. Most of them are there because of the imbalances in the power network. By controlling those imbalances and distortions in real time, the power is delivered as opposed to wasted. From an energy savings perspective, universally, when you install the power controller, capacitive loads like lighting and computers are going to see a 10 to 15% reduction in energy consumption. Inductive loads, motors and compressors, will see a 20 to 25% reduction. In recent defense testing, we showed on a 3-phase motor a 60% reduction in energy consumption. Now, what all of this means, a 100 kilowatt motor is going to need 100 kilowatts. Today, in an uncontrolled environment, it is pulling 150, 160 kilowatts, and it's wasting 50 or 60 along the way. When you turn our device on, it pulls 100 kilowatts, loaded or not, all the time, perfect RPM. And this is the advantage of digital power delivery, is eliminating the waste in the network. Now, energy savings is very valuable and it is very desirable, but it is not the most important part about this technology. It is a large part in how it is paid for, but there's two sides to the equation. Assets that receive poor power quality perform poorly. Like any fluctuation in the power is a or in the electricity is a fluctuation in the power in the device. It is energy. The device is not designed to withstand the fluctuation in power, so it reacts who knows how anyway. Right? When you turn on software-defined electricity, like what you see immediately are the devices that are in the network that were designed to operate a certain way are now able to operate exactly as they were designed. Motors have a specific RPM associated with them. But in an uncontrolled power network, when you load a motor, it droops. If it's 1375 RPM, it drops down to maybe 1100. If you completely unload the motor, it floats above the 1375 into the 1400. And that is an exquisite example of wasted power. When you turn our device on, that motor and all motors in that network will always run at the rated RPM, whether they are loaded or not. Servers for data centers. The purpose of a server is to transfer data. But there's a packet error rate and a retransmission rate associated with transferring data. When you turn on software-defined electricity, now that packet error rate and retransmission rate plummets to well below 1%, because now there's no fluctuation in the power and those servers are able to do exactly what they were designed to do without having to worry about the fluctuation. We have gone into radar and RF antennas. Radar will double the distance that it can detect devices because it eliminates the ground current at the receiver, increasing the effective aperture and detecting further, 2.2 times. A similar principle is true with RF signal. RF signal, by reduced ground current and phase balancing, can propagate RF signals up to twice the distance because of lack of noise. This is all related to the clean power. So the three areas that we focus on are harmonics and power factor, reactive power. But one of the most important parts is, and that's traditional power quality, is harmonics and power factor, right? Voltage. But phase balancing, equal balances across phases, results in direct loss. If you have an imbalance in phases, you have neutral current in the network downstream, and you have eddy currents in the transformer upstream. And so power quality needs to include all three: harmonic, power factor, and phase balancing, all in real time. If all three of those are addressed in real time at once, then you have stability in the network. That is the root cause of instability. And then I'll just quickly, some of the other benefits are increasing the power infrastructure asset capacity, like transformers. When there's an imbalance in transformers, the capacity of that transformer is limited to the highest used phase. When there's a perfectly balanced phases, now you can maximize that transformer. You can add more loads on the end. The same thing is true for generators. A generator produces a certain amount, but it's not ever running at tag value. It was designed to run at tag value, but it can't. As soon as you put a generator in a network that is cleaning the power the generator is producing, all of a sudden that generator will operate at tag value. So increasing power asset infrastructure is incredibly important from a just for efficiency perspective, efficiency of power deliver at the macro level. Going on, these devices are all edge computers, unable to, they connect to the internet, again, serial port out, so it provides power network cybersecurity. Oftentimes, with things like Stuxnet out there, where there are intelligent viruses and intelligent, smart inverters and everything's becoming internet connected. And the threat of the future is getting into a network and slowly changing frequencies and adding harmonics and doing all of these harmful effects to the power quality, because the result is loads will shut down, facilities will shut down, break, there's downtime. Right? This device is cleaning the power. Every 900 to 1200 nanoseconds, the power is going right back to synchronization. And so there is no ability to put a device in and have it affect the power, because it's always going to be corrected in real time. And that's a huge advantage. Going on, there's the concealment of electrical signatures. Right now, neutral current sniffing or electromagnetic EMI detection is very easy to do from far away. Right? What this device does is it zeroes the ground current, it zeroes the neutral current. It reduces the EMF, it reduces the eddy currents in the upstream transformers, it reduces the signatures related to uncontrolled power, which is also very valuable from a military perspective, I guess. And then going on, there's surge protection. We have a very novel way to address lightning strikes in real time, all the way up to EMP within threshold limits. Obviously, within the cone of destruction, there's nothing that can be done. But outside the cone of destruction, we can divert surges so that devices can restart. And that, again, can deliver incredible value. And then finally, the non-intrusive load monitoring and predictive analytics. By embedding real-time computing into the network and identifying the differences among electrical signatures and tracking those signatures over time, now you have a full historical visibility of all of the assets within a network and the deviation over time. A deviation in an electrical signature is nothing more than the internal components wearing out or no longer working the way they were. It is the most, it is the closest, the root visibility into changes in the network. Oftentimes, we'll talk to people that say they have thermal sensors on their network, and that on their motors, say. And a thermal sensor will alert you 2 days or so ahead of time that the motor is going to fail. Then we'll talk to more sophisticated business owners that don't put thermal sensors on, they put vibration sensors, because a vibration sensor can detect what the thermal sensor can detect, but weeks earlier. We've seen some clients that even buy ultrasonic sensors so that they can detect the vibration even sooner. But our whole contention is, when that event originally occurred, there was a delta in the electrical signature. And that delta has continued and continued and continued until then it can be detected. The wear and tear has occurred so much that it can be detected by ultrasonic. And then the wear and tear continues and continues and continues, and then it can be detected by vibration, and continues and continues and continues until it can be detected by heat, and then eventually it fails. So this method is a thumbprint on all predictive analytics and non-intrusive load monitoring going forward. And that's a huge advantage as well. Now, I'm going to get into the demonstration. I took a screenshot here just so I can walk over what the dashboard looks like. On the top left, this is in our facility, and I'll turn it on and off and let you guys see it. But just so you know, on the top left is the voltage for the network. Just under that, you have the current. Under that, you'll have the first 11 harmonics on each phase. This is fundamental. And then 1, 2, 3, 4, 5, all the way through 11. The yellow is the average of the harmonics, and everything on this graph is color-coded according to phase. In the top right, you will see those phases. Black is phase 1, blue is phase 2, red is phase 3. And let me move this out of the way. You'll see the parameters, the electrical parameters, so current, voltage, harmonics, voltage, harmonic factor, power factor, all streaming, and then the averages. The phasor diagram here shows the real-time relationship between current and voltage. And then you have your graphs over time. This is your active power over time, harmonics over time per phase, and then power quality over time per phase. When I mentioned prior the phase balancing, we have our own internal metric. This is power quality rating. What we've done to create this metric is a combination of harmonics, reactive power, and phase balancing. So in this screenshot right now, our facility is purchasing 100% of power, but it is using 52% as electrical energy. It is wasting 48% as heat or vibration somewhere in the network. And so what I'll do now is, if you give me a second, I need to switch over. Now, what I have done is this is our live dashboard that you can see, and I have it running through YouTube. So it's just a live stream on YouTube. What I will do now is I will turn off the light in the room I'm in. There's a slight delay because of the YouTube, but what you will see right here in the current over time is the reduction of current from turning out the lights. Now, something else also turned on there. So that wasn't as clean as I wanted it to be. I just turned the lights back on. I think I picked a poor time to do this. I'm just going to do it again just to give you guys so I'm going to turn it off now. Then I'm going to turn it back on again. That should. There we go. Okay. Sorry for the delay. All right. So now what I'm going to do is I'm going to actually turn on software-defined electricity. And what you will see is the current and the voltage immediately come perfectly in line. You look at where it's crossing the zero axis. Perfect, perfectly in phase. The harmonics are now being mitigated. This is a logarithmic scale, and now they're all hovering around 1%. The relationship between current and voltage is actively being managed and synchronized. And then you can see how the active power looks over time. From a utility perspective, you will be a 100% active load. This device is a reactive power generator among many things. And reactive power never goes back onto the facility. So from a concealment perspective, also, there's no signature except for kilowatts coming out of the facility. And then you can see the harmonics are addressed in real time, all actively. And then, of course, the power quality. Up to the power quality rating, you see now we are buying 100% of our power. We're using 95, 96%. What I'm going to do now is just turn the device on and off for a few seconds. There's a lot on this dashboard. So just to give you guys a perspective on, one, the speed of it, but two, take a look. I mean, just see the whole thing. And I'll just do this for a few minutes. Turning it on. I'm turning it off. Some things that I will point out on this right now is if you look on phase 1, it's 3 amps. You look on phase 2, it's 14 amps. And look on phase 3, it's 3 amps. It's a small amount of power in this facility just because it's so early in the morning. But when I turn the device on, what you'll see is it immediately averages out 6-7 amps per phase. Now, the way we're doing that is within the device is a DC bus bar. We are pulling the power equally from the upstream transformer. We know that there's, in this moment, we know there's 21 amps that's required in the device knows there's 21 amps required in that moment. But it's 3, 14, and 3, or whatever the numbers were. So it pulls the 21 amps equally on all 3 phases and then redistributes it onto each phase so that it perfectly distributes the power and there is no neutral current. That function is what is mainly missing today, is that real-time phase balancing, in addition to some of the other stuff. But that is a huge advantage on power distribution. When there is no imbalance in the network, it significantly reduces the power quality issues. As I mentioned, the eddy currents in the upstream transformer that exist will go away. Like all of a sudden, it's no longer there because of the imbalance or the balance. I'm turning it on. And now I am turning it off. At this point, I think it's probably appropriate to open it up for questions and answers. And if you would like me to turn it back on and turn it back off, I have no problem doing that. I just want to make sure that you all get your questions in.
Hello.
Yes.
Hi, Chris. I think it's not a webinar, it's a magic show. Electrical magic show. Really great.
Electrical. Thank you. Thank you. It's a very fascinating technology.
Yeah, very true. And I can see it's a amalgamation of electrical, electronics, computer, instrumentation. So many things are working together.
Yes, yes, that is the biggest differentiation between what is existing today in the network. If you have harmonic filters or power factor correction, I mean, it's just AC capacitors and transformers. That's pretty much it. What we have figured out is just a principally different way to address it. As I mentioned, it's the same concept. You need to inject capacitance or inductance into the network. It really does come down to when and how much. And the more precise you are on that, the more efficient the power delivery is. And I believe we found the nexus of that.
Yeah, very true. We'll wait for some questions. I haven't seen any raise hand. Maybe people are again observing. Yeah, one hand is raised. Amit sir, can you unmute Narendra Dwivedi sir?
Yes, sir.
Chris, there is one question, Mr. Narendra Duvedi. Sir, please go ahead. Narendra, sir? Amit, sir, have you unmuted him?
I think he's not going with audio. Come to unmute him.
Narendra, sir, I think your audio is not switched on. Meanwhile, there is another hand raise, Mr. Reddy. Amit? We are unable to see any that mute symbol against them, Amit, sir.
I think it's because of audio. Hello?
Is it due to broadcast is on because their sound is mute? If you have any settings, you can change so that people can ask.
Yeah, just fine.
Meanwhile, Chris, there is a question in question answer session. Shall I read it to you?
Yeah, here, let me, yeah, if I can, I can't see it for some reason. So, oh wait, under chat maybe.
You can.
Can you read it to me, please?
Mr. Mohammed Tariq is asking, you mentioned that you have a DC bus bar that pulls equal current from the upstream supply or transformer on all the three phases and adequates this imbalance in current on all the phases.
Yes.
In only that much he has typed. Maybe if you can repeat that again, how this current equalization takes place using DC bus. I think he might be asking that.
So the law that this device focuses on mainly is Kirchhoff's law. That is what it's using, equitable distribution of current. Right? I don't know how to answer it much more than that. The control part allows us to convert AC to DC at 98+% efficiency. So what the entire process is pulling the power, converting it, storing it into the DC bus bar, and then reconverting it, and then distributing it as AC on each phase. Right? That's the process of that. I don't know how to answer it much more than that. Unless it's a more specific question, I guess.
We are checking because there are many hand raised. Hello. But we are unable to, because there is no mute unmute symbol, we are unable to see that. Unmute.
So I see a couple questions here about, I think, flexibility. So one question about Indian voltage. This technology, one of the advantages is it's small power electronics at the circuit board level. As I had mentioned, this box next to me, it weighs maybe 20 pounds and it corrects 60 kilowatts. It doesn't need air conditioning. The next closest device that does the same thing is the size of a refrigerator, maybe 2. So it's a significant reduction in size. But the other advantage is this technology presently is scalable up to 26 kilovolts using commercially available off-the-shelf transistors. And so we can, the software-defined part, we can design devices for any power or any voltage up to 26 kilovolts. And so right now, this device is 240, it's US standard, it's 60 kilowatts. We're presently working in Europe to develop a 220 volt, I'm sorry, I can't remember the voltage, but the European standard and 50 hertz frequency. We will begin, so I see the 415 volt. We have a 480 volt that we're releasing in the United States shortly. And then we'll continue to scale up into the secondary transmission level. We'd like to be in substations by middle of 2021 is what we're shooting for.
Okay. Amit sir, I think we can unmute Narendra sir. We can see the symbol unmute there. Can you try, Amit?
Hello.
Yes, sir. Go ahead.
Hello.
We can hear you.
Okay. Good afternoon, good evening, whatever it is. It was a very nice presentation to hear from you. My question is, apart from predictive algorithms, how does this technology differ from an active harmonic filter?
Yeah, so the real harmonics are very important, but they're no more important than reactive power and phase balancing. The real key, the algorithm, is it's not individually addressing them, it's addressing all of them at once. It's a single algorithm. And that's really the key. Like conversion, anytime conversion occurs, anytime adjustment occurs, it needs to be a single act, whatever that is. And this is what we're delivering, is precise electricity control, right, in real time.
Yeah,
that's it. It's all the power's on the
typical active harmonic filter current capacity can actually be divided between harmonic compensation, power factor compensation, as well as load balancing. So it is programmable. So for a fixed load, fixed load in the sense a defined load, probably an active harmonic filter can take care of electrical part of what all is being demonstrated in this webinar. Apart from predictive maintenance obviously is not there in those algorithms, or signature analysis doesn't exist in a active harmonic filter. That was my one question. Second question was, what would be the approximate loss in this system per kVA or per ampere or whatever?
So on the so yes, there are systems out that do power factor correction, harmonics, and phase balancing. The question is, what is the efficiency of that device? And so, again, this device is 60 kilowatts with perfect conversion and harmonics and reactive power and phase balancing. It uses 120 watts. So the 98% efficiency of conversion of power, of correction of power, this is the biggest, most demonstrable difference. You're going to be in a footprint that is a tenth the size, and it's a fraction of the power, and it's more improved. From the predictive analytics, your question, the reason why predictive analytics can occur is because of the intense analysis on the electrical signatures in real time. The device itself automatically, as soon as you turn it on, it instantly knows exactly how many loads are in the network and instantly starts to track every single signature. It has to do that to be able to match supply with demand. It needs to know exactly what's going on in the network. From a human perspective, like, you can turn on a program and say, do you want to add loads? Yes, I want to add this motor. I want to call it refrigerator motor. I want to add this television, call it living room television, or whatever. At that point, the system will continue to track it internally as it knows it, but it will report it as whatever the human puts the information in. And that's it. The system itself is automatically tracking. Like for humans, it really is just identification and then representation on the user interface. That's the biggest difference. We over-focus on the computing so that the work itself is done with the utmost efficiency, and the analytics are all available.
Okay, thank you.
Yes, sir.
Thank you, Narendra sir. Thank you, Chris. Can you see the second question, Shivashankar Nagarjan?
Is it an amalgamation of electrical electronic?
It is indeed innovation at this best. Could you please define how one could establish the capacity and configuration of the product to suit the installation requirement?
Yes, no, that's a fantastic question. We have tried to make this as easy as possible. It is simply on power consumed. So a facility consuming a megawatt of power would just need a megawatt of protection, is how it works. So the device itself, as we said, this is a 60 kilowatt device. In the 240 range, we created the 60 kilowatt first. This is our first device. What we have learned is that there is a need for maybe a 30 kilowatt device in the 240, but that's about it. In the 480 range, the first device is 120 kilowatt. I'm sorry, it's 90 kilowatts. The next one is 240, and then we go up to 500 and so on and so forth. So the model that we've conceived of is distributed control throughout the network, so that if any one doesn't work, gets pulled off, gets turned off, there's still control in the rest of the network. And that's how we've designed this.
Yeah, thank you. Should I read next question?
Please, yeah.
Yeah, Mr. Deepak is asking, as we install this system, if there is an increase in power unit consumption, how to go about? Since you have done it for 60 kilowatt and now they have increased the load to 750 kilowatt, that industry.
No. Excellent question. You guys are asking very, very good questions. Yes, so let's assume you put the 60 kilowatt device in a network with exactly 60 kilowatts. Then what you're going to see is the PQR is going to maintain at that 98, 99%. As soon as you add, say, 10, 15 more kilowatts, and it goes above. So now it's at 75 kilowatts. Because the device is in parallel, it will continue to clean that 60 kilowatts. And so what you're going to see, the difference you're going to see is now that PQR is going to start ticking down. It's going to go down to 95, 94, 93%. And that's really the biggest difference. We have a system built in that once you exceed the power requirement, it will alert you and say, hey, listen, you may consider getting a bigger device or a second device or whatever. But that is also the advantage of it being in parallel. It's not a single point of failure. It will continue to work whether it's overloaded or not at the same level.
Yeah, thank you. Next question. Mr. Vaibhav Mahalle is asking, what is the minimum and maximum rating of the PQ correction device?
The minimum and maximum. Well, this particular device, when you say the minimum and maximum rating of correction, is that like how far can it correct? We have full control of electricity, so from 0 to 0 on reactive power. If your reactive power is 10, we can bring it up to unity in real time. So there's no limit on the corrective rating capacity of it. It's full corrective capability.
Okay, thank you. Next, Mr. Rahul is asking, at every step, rectifiers and inverters are required for AC to DC and DC to AC conversion. So is it cost effective? Means in general, electrical engineering, I think is.
Yeah, so what we're doing is principally different. So as we compare in the United States, if you go to like a residential inverter is maybe 3 feet by 3 feet by 6 inches, and it goes on the wall. It's maybe 60% or so. I mean, not 100. I mean, 60, about 2/3% efficient, and then it degrades over time. So in year 10, it's nowhere near as efficient as it was in year 1. Right? That's traditional inverters as they're done today, mechanical conversion of power, rectifiers, etc. What we do is principally different. Our inverter is the size of a cigarette pack. It is 98% efficient, and it does not degrade over time. And so from an efficiency perspective, it always boils down to efficiency. What is the efficiency of the method you're doing today versus the efficiency of what we're doing? What is the size footprint of what is being done today versus the size footprint that we're doing? And whether it's transformers, whether it's inverters, whether it's generators, transmission equipment, or consumption, Everything can be shrunk now. All assets in the entire power grid anywhere in the world have been designed for the last 140 years for fluctuating power, for uncontrolled power. And so the future with controlled power means we can reduce significantly the resources embedded in our power network. We can reduce the copper wire, we can reduce the size and windings in the transformer, and so on and so forth. And that is really the tectonic shift that we're delivering. It is a principally new way to control electricity, and that applies to all aspects of the grid.
Okay, thanks. Next, Sean is asking, how does this device differ from an active filter? They all offer fundamental harmonic reactive compensation as phase current balancing. You have answered this, but again, a quick recap.
Sure, yeah. I mean, it's really efficiency and precision. Our error-free data acquisition provides us with a fundamentally different foundation, right? We know exactly what it is. It is what it is. And that changes the game, really. Existing power quality related devices, it says active power, but that just means it's shifting faster. It's not static. It's active, meaning it changes, right? But those changes, they're just not fast enough. They're not efficient enough. That's it. So it really is just a new category. It's like there's static, there's active, and then there's actual correction. We have actual correction instead of, it's really compensation is what you're talking about. The present method is simply compensation. The best analogy I can give is if you squeeze a balloon, the balloon goes and it doesn't pop. It goes through your fingers. The air has to go somewhere. When you generate electricity and put it onto the grid anywhere, that energy has to go somewhere. If it doesn't go to the load, it's going to be released as heat or vibration. That's it, right? And so active filters, you see, not only do you put the active filter in, but then you have to put air conditioning in too, large fans. That's not efficient. There's no efficiency. This device, it has 2 fans on the side. They don't even run unless a lightning surge is coming through. So it's all about efficiency, 100%. That's the biggest difference.
Yeah. Thanks, Chris. Now, next, one of my friend, Mr. Hari Bala, is asking, good technology, should we use this product at the incoming supply or at our individual load ends?
No, that's a very good question. This present product is just a load side device. Because it's rated for power, if you have a 60 kilowatt load, you would want to put this device close to that load. If you have a panel like this is with 45, 50 kilowatts spread throughout the entire panel, then this is where you want to put it. So the closer you are, the more efficiency is delivered because there's obviously line losses involved. But that's, again, it goes up to that PQR where if you put it in a network, it's going to take, look, right now it's 15. So we're buying 100% of our energy. We're using 15% as electricity. We're wasting 85%. That's just crazy, right? And so I guess that's a big difference. Right?
Yeah, thanks. Next, we have Shailesh Mahindrakar, one of my colleague. Nowadays, we do have solar generation. Does your device suit to use where power flow is bidirectional?
Yes, no, another excellent question. So we envision so that right now there's a move in the United States. I'm not really up to date with what's going on in India, but there's a move to allow utilities to control smart inverters so that they can adjust reactive power from a centralized way. What this does is this harms the consumer. This is really what happens. They're the ones taking the losses there. What we're advocating for, every device, whether it's an inverter, whether it's a transformer generator, whether it's reclosers, They need to be a net benefit when added to the network. They do not need to add instability problems. If they add instability problems, it's not the proper method. And so for what we envision is this device being embedded in inverters, being embedded in distributed energy resources in general. Because when you, on the inversion process for solar, there's a whole spectrum of problems. There's an interconnection problem. This is one of the biggest issues in the United States right now. We have 10...
Because they are similar, maybe we can reply them later. Next question, we'll take last 3 questions now. Next, Pramod is asking, can this device protect from transient surge?
Yes, absolutely. It's a very novel way to protect surges. Like we have, as I mentioned, there's a source of inductance and a source of capacitance in the box. We have developed our own proprietary materials and cores, and this is the injection of the inductance. When a surge comes into the network, and it doesn't matter the size of the surge here. The analogy I use is the ocean. When a tsunami comes in from the ocean, the first thing that humans recognize is the water recedes. And the further the water recedes, the larger the wave is coming in. The exact same thing is happening when there isn't a tsunami. And that's what waves are. It's receding and then coming up, receding and then coming up. The exact same thing is true with electricity. When a surge is coming, there's a recession right before the surge. And what our system has been trained to identify is that recession and identifying how large the transient is coming before the transient actually gets there. And so in preparation of that, it will divert all of the transient. It can cut it in half and separate it and dump it into our cores. And this is what I mentioned with the fans on the side. They don't even turn on. It's 120 watts of power. They'll turn on every now and again if it's a hot day. But as soon as that surge is detected, this system is not only air cooled, but it's oil cooled and water cooled as well. And all systems start going full blast, dumping that energy into the cores, and then releasing it as heat, so that it's not thyristors. It's not when you today with lightning protection, with surge protection, you don't know how much you have. And after a surge, you have half as much as you did. That's crazy. You need to know that you're protected at all times. And so this system is non-degrading lightning protection. That's a very important component. Yes.
Yeah. Thanks. Hey.
Mm-hmm.
Thanks, Chris. Last question.
Yes, sir.
Last question. Mr. Suresh Mali is asking, how cyber security is achieved?
Yeah, so the device itself is it's not internet connected. The control function of it is completely separate. The reporting function is simply a serial port out. So the concept, I've been turning software-defined electricity on and off for this demonstration, but we do not sell devices that are able to be turned on and off. That's fluctuating power. You shouldn't do that. We do it because we know the environment, we know the loads, we know everything, but it just shouldn't be done. And so that's when we deliver them to customers, it performs the correction. It takes your dirty power, it turns it clean, and then serial port out reports data. So there's no way to hack into the device and even get into the control space. It's simply data out, reporting on what has occurred. And that's it. The devices are, actually, I see a question here about maintenance too. That's also a good question. Let me just highlight that. There, outside of brushing the fans, there is no maintenance. It's set it and forget it. We originally thought the very first components that are going to degrade in this device are the bank of DC capacitors that we have. However, we've had one running now for 12 years. We took it offline to open it up and investigate, take a look at the DC capacitors and understand how much wear and tear has happened. we originally said these would last 10 to 12 years. Now we're pretty happy saying they'll last 15 to 17. And we'll do some more testing on that in a few years to see if that's the case.
Yeah, thanks, Chris. I think we are perfectly ending at time at 6:45, as we have said. Uh, uh, I would like to request our principal, Mane sir. Sir, are you there?
Yeah, I am there.
Would you like to add some concluding remarks?
Yes, yes. A very wonderful presentation and actually a state of the art equipment. I think that we were amazed of seeing what inventions you have made. So a great thing. Once again, thank you, Chris, for your presentation. Nice presentation. Thank you very much. And also, I would like to thank Shelar sir also for coordinating this activity. Thank you.
Yeah, thank you, sir.
Yes, thank you very much. I sincerely appreciate it. And thank you
Yeah,
very
so
much, Sachin.
overall, at the end, I would also, on behalf of AISSMS Institute of Information Technology and Power Quality Cell of Electrical Engineering Department, I would like to thank first Chris for giving his valuable time and explaining all the things in such a lucid manner. The so big complex problem, but you have explained in A plus B plus C. Of course, as you said, there is lot many things is going on, but it's really a very different magic, and it's really here we have seen that. Power quality field and reactive power, it is saturated. Everybody is saying only capacitor, APFC, and active harmonic filter, but you have gone way ahead. It's just like Elon Musk, you have gone into that electrical field. So thanks a lot, Chris, for giving wonderful presentation. I would also like to thank all the participants for your patience listening. I would like to thank our HOD, Professor Mrs. A.D. Siralkar, our principal, Dr. P.B. Mane, and our management for giving this opportunity to me. Thanks to all. Thank you, Chris.
Yes, thank you all very much. I sincerely appreciate the opportunity to speak to you. I will be happy to answer any questions if there's any follow-up after this via email or whatever. But thank you so much for the opportunity.
Yes, sir. And all the participant link is given in the chat for the feedback. Please fill up the feedback. You will get the e-certificate on your email ID. And if there is any study material later on, we'll be sharing it on your email ID. Thank you.
Wonderful. Thank you.
Amit sir, are you there? Amit sir, have you put the feedback link in YouTube also?
Just a minute, I'm just putting.
Sir, I am unable to put anything in the chat. Can you put the link? Because chat is blocked for me. I had put it earlier, but again, can you put?
Yes, sir, now we can put, sir. Send it to me also, sir.
Yes, sir, I will send it to you. Yeah, I have sent it to you also, and again put into the chat window.
Yeah, I'm just sharing.
Thanks to all the attendees. Please give your valuable feedback. Sir, we'll wait for 5-10 minutes. so that if any participant has any problem, we can solve. Amit sir, recording is over now. You can stop recording. Thank you. Yes, participant can leave the session. We'll be waiting for 5-10 minutes if for any other participant has any problem. If you have given the feedback, you can leave. Thank you all.